Okay, so I would actually be talking about some of our recent results on this ferroelectric material, which is indium selenide, and if time permits and if he graces, then I'll probably touch on this next part, which is on antiferromagnetic and IPS3. So we have been looking at these systems using Raman scattering, basically trying to understand if we can sort of create new types of material system. Though it looks like, okay, one is ferroelectric and other is magnetic, what does it have to do with what we are talking today? So basic idea is, as we see over the top, okay, I'll come to that. So this work is basically done by Shashwata here and Devesh, which is here. And there are some simulation work done by Ravi Shankar and his team. And thanks to the various agencies who have been funding us generously. Okay, so 2D material, I probably don't have to get into that. Those who had listened to Professor Arindam Ghosh would already have got an entire picture of it. Anyway, so just quickly, the covalent bonds being present in the individual layers and the van der Waals bonds being present in the out of the plane makes it very easy to peel off and then create as thin or thick number of layers, sometimes very controllably, and then create various kinds of structures that one can think of. And there's a zoo of 2D materials that can be worked on, and he was also quoting almost about 2,000 materials that can be sort of exfoliated and can work on to design new material systems. And based on that, as we thin down, one knows how the electronic, optoelectronic properties evolve. And also on the magnetic systems, the magnetic interactions also are influenced by the layer thickness. And based on that, there are many different angles or aspects these 2D materials have been seeing potential applications. So one of these interesting part is where you can actually design and create various kinds of 2D materials. So that's where I connect to my the title, where we have ferroelectric and then magnetic system. Basic intention is to create multiferrocity in this engineered system. So while doing that, we actually have learned something new, and that is what I'm going to share with you. All right. So with that, so about this indium selenide, which is ferroelectric. So ferroelectric, when we say, basically mean that we have these electric dipoles in the individual layers, and of course, this is taken from 3D picture. And we eventually have a PE loop, which is hysteretic, and the remnant polarization will give us the on and off states accordingly, which can be used for applications. Now, you see, this is an example taken from boron nitride, hexagonal boron nitride. If the boron nitride layers are stacked in the parallel configuration, which is the first stacking here. So that gives us net zero dipole moment. But on the contrary, if you have a slide by about 1/3 of the lattice constant, then it gives this anti-parallel stacking, and that's where we actually see some polarization adding up to it. And similarly, there are whole variety of other 2D materials that have been drawing attention over time, apart from the historic 3D systems. So indium selenide is something that I'm going to discuss. And so indium selenide, as you can see, this is basically, every individual layer has this quintuple layer, where there are 3 layers of selenium and 2 layers of indium. Now, something very important that I want to make your attention here. So you can see this indium is tetrahedrally connected, and this is octahedrally connected, these 2 indiums. So that makes this structure very unique. And this is what is the monolayer of it. And based on how this one layer is stacked with other layers, it can actually give these 4 different polymorphs. And there are other polymorphs as well, which I'm not going to talk today. So in this polymorph, so this stacking, which we call this alpha, and the other is beta. So you can see in alpha stacking, we have this tetrahedral and octahedral coordinated indium stacked as 2 or 3 layers. Then this becomes 2H structure, and this becomes 3R structure. But on the other hand, in the beta, what we have is only octahedrally coordinated indium. So this is the distinction between the two structures, and the correspondingly the other polymorphs where the 2 layers or 3 layers would be stacked. And the alpha systems are ferroelectric. That basically because it breaks the inversion symmetry, and there are various reports on its ferroelectricity in the literature. And the beta phase is basically paraelectric, that because it loses the inversion symmetry. All right, so we have certain questions to start with. We basically wanted to look at the various polymorphs of indium selenide and how it evolves from one structure to another. And that's what we started with the experiment. Now, in terms of Raman signatures, if we grossly want to see, so this is alpha 2H structure and corresponding Raman signature. And this is alpha 3R structure, the 3-layer stacking, and this is 2-layer stacking. If you notice, the high frequency modes are almost the same, except the low frequency band, which is shaded here. So you have only one component, and we have 2 components here. So this is the distinction of the 2 structures for 2H and 3R. And as compared to the alpha stacking, the beta stacking is here. You can see the spectrum itself is quite different. And that's also connected to its, what do you call, the metallic nature of the beta phases. So here you can see there are 2 peaks here. And these 2 peaks basically corresponds to the 2H structure, and single peak connects to this 3R structure. So these will be the signatures for us to identify whether we are in the alpha 2H, alpha 3R, beta 2H, or beta 3R. And let's proceed now. And these are the calculations done by Ravi and Mitanshi. So this is the various vibrational modes that are responsible and would be sort of our signatures to look at the transitions. So what we start with, we start from room temperature stable phase, alpha 2H phase. And as we heat this up to about 480 Kelvin, it starts to undergo the phase transition to the beta 2H phase. And if we limit our temperature to about 500 Kelvin, it retains the 2H phase. And if we cool down from that temperature, it comes back to 2H. Now there is a hysteresis. Here is the color map for this to look at very clearly. So this is the heating cycle. You can see about 470 Kelvin, the phase transition happens. And in the cooling, the phase actually comes back. It's a reversible transition, but the reversibility happens at a lower temperature, about 370 Kelvin. So about 100 degrees is the what do you call the hysteresis, hysteretic transition, the width. The hysteresis is about 100 Kelvin. Now, the same way, if we look at now the same alpha 2H, and if we extend it to much higher temperature, here you have gone actually about 520 actually beyond, what we see now, it not only goes to beta 2H, but actually it further goes to the 3R stacking. Okay, so at much higher temperature, it goes to the 3R stacking. And if you cool it down back, it does not come back to 2H structure. Okay, so once it has transformed to the 2-layer structure to the 3R structure, it retains. So that's the irreversible transition as compared to the previous reversible transition. So we can sort of summarize this in this way. Depending on the temperature that we are actually going to, it actually can have a reversible transition from alpha 2H to alpha beta 2H. But if you go to much higher temperature, then we hit upon the irreversible transition to the alpha 3R phase. So now this is, again, looking at how the alpha 3R phase will behave in this thermal cycle. So alpha 3R phase individually would also show a reversible transition with much fat hysteretic loop in this. And so now okay, another interesting part of this, there is a wrinkle that gets formed as we sort of do this thermal cycle. And here you can see the wrinkles developing. I think I have a video as well. So from this video, one can see. So this is the starting. This is basically this is the starting picture, which is very clean. And then as it goes the thermal cycle, it forms the wrinkles. So it's not only that the structural transition happening, there is also strain that generates, and it leads to formation of wrinkles in the structures. Okay, so these are the calculations done by Ravi. So these are the various structures using DFT and molecular dynamics as well. And what we learned from there, that the ground state energy of these phases follow this sequence, where alpha 2h is the lowest energy, and alpha 3r follows that. But they have very comparable energy range, but the beta 2h and beta 3r are actually much higher, and they're almost about 100 degrees away. Here you can see the phonon dispersion relations. So both the alpha 2h and alpha 3r, they show stable phonon dispersion relation, but the beta 2h and beta 3r, the blue curves you can see, they are unstable at the 0 temperature. But only when you go to much higher temperatures, they stabilize. So that basically supports what we could find experimentally. Now, the mechanism that we basically are putting forward, how the structural transition happens, I mean, basically the rearrangement of the atoms happen. So this, you can see this is the tetrahedral coordination. And these upper layer atoms in the quintuple layer, they basically move by about 1/3 of the init cell to form the new structure. And that's how it goes from the alpha 2h to beta 2h, and then eventually from beta 2h to beta 3r, and then comes back to the 3r phase. Then we asked, what if we actually thin down these layers? So when we thin down, how much time do I have?
10 minutes.
Okay, nice. Fine. So, so when we thin down, we again relooked at these transitions. Wait a minute. Relooked at these transitions, and we could see that an interesting observation here. You can see I was telling that the phase transition happens right about 470 Kelvin for the alpha 2h to beta 2h, and this you can see, this is for a very thick film. I mean, of course, everything is very, very thick, but still there is a difference, significant difference in the thicknesses. So this is about 250 nanometer thick film, which you can see the transition happens somewhere around 470 Kelvin, 450, 70 Kelvin, and then there is slight mixed phase in between, and then it goes to the complete beta phase transition. On the contrary, if you take about 100 nanometer thin film, there is no phase transition happening up to a temperature of about 550 Kelvin. What we attempted was we tried to go beyond that temperature, but then the sample gets degraded. So we couldn't establish the phase transition for the thinner flakes. Then we did another round of experiments. What we did was, this is also another interesting aspect. When we did this on a thinner flake of 3R, I mean alpha 2H to beta 3R, then we cooled down. What we saw is that there is an intermediate phase for some thinner flakes that happens to be the beta prime phase, and that's different from the structures that I was discussing. So the beta prime phase that we believe is basically another distorted octahedrally coordinated structure of this system. So this part I'm concluding that we have reversible or irreversible transition depending on the temperature limit that we push it to, and these are the different structures that come to. If I have about 3 minutes, then I can quickly talk about what we actually looked at in NiPS3. So in NiPS3, we know at low temperature it is antiferromagnetic. And the antiferromagnetic ordering, as you can see, the spins are put in the red and this, the black colored arrows here. So they basically are in a zigzag chain, they're anti-parallel to each other. And there are 3 possible configurations that it can actually take. So that way, if I draw this Neal vector, so I have this horizontal 0 degree oriented, then I have 2 other orientations which are 120 degree each from each other. What we did, we actually looked at this using Raman, and in Raman we could actually map these 3 different orientations of the spin. So here is the Raman signature in the antiferromagnetic structure, where you have it what you call the 2 magnon mode along with the various other modes. And most important feature that we actually carry here is the spin phonon coupling. And this spin phonon coupling has an anisotropy depending on whether the vibration of the mode, I mean the atoms, are along the direction of the spin or normal to the direction of the spins. So that will give an anisotropy in the spin-phonon coupling, and based on that, this particular mode will show a splitting, and that splitting becomes our signature to understand this magnetic ordering as well as the spin orientations. So we looked at what you call the angle resolved polarized Raman, and based on that, here is what. So these are some calculations that we had to do. I'll show you the results here. So this is the flake, which is roughly about 12 nanometer thick, and these are the various spots where we looked at. Of course, there's a mapping, and these are the various Raman spectra, and then we carefully analyzed the data, and what we can see that these two modes show this lobes, and these lobes would basically orient depending on the spin orientation, and here you can see the three different orientations. So this is one orientation of the spin, this is another orientation of the spin, this is third orientation of the spin for the same flake. All right, I think with that, I would like to stop here. Thank you. I think I managed to be on time. Brijesh will not be unhappy.
Yeah, Surajit, I have a question. So in this beta phase, you do see imaginary phonon modes, correct?
Yes.
So have you tried to freeze the mode and then it is going to some other symmetry?
Right. It actually, so when he freezes the modes, it actually leads to the other structures.
Yes.
So that is what was connected. Then he also looked at using MD to sort of stabilize the structure, and then he figures that there is a temperature required to do that.
But you are not seeing the same in temperature dependent X-ray?
We did not do that temperature X-ray.
Okay.
We did not do that.
Fine. Yeah, thank you.
So actually these flakes are so small, we cannot do routine temperature X-ray. We may have to think of some other ways out.
It's a quick announcement. Somebody has dropped his key. So if you know if we have lost your key, we'll get it from.
Yeah, I saw it sometime back.
Okay, so just a small maybe comment, not question. With Abhishek Mishra from IIT Madras, we are studying some RESE2 because it also has n number of polymorphs. So when we were trying to examine the potential energy surface, we found many local minima. Basically, the structure turned from one minima to other minima. I felt that your thermal energy, while you are applying the temperature,
Yes.
the system is tunneling to one minima.
Yes.
But when you are changing the decreasing the temperature further, some other dissipation or something happening, the system is not going back to some other minima. I think that's
So likely that there are some potential barriers, and it's only like a few hundreds of degrees apart in terms of energy, and that the transition happens. Some of these transitions are reversible, some are not reversible.
I think that due to decrease in the thermal energy, maybe some other dissipation or something. That's why the reversibility is not happening.
Possible.
That's my observation.
Okay. Yeah. Thank you.
So what happens if you cool down below room temperature?
Okay, we did that. So, let me talk about both the phases, especially the alpha 2H to beta 2H. Of course, it has come back to the alpha phase. The other one, the 3R stack, it remained in the 3R stack down to 80 Kelvin. We did not go below 80 Kelvin. Then we have to try with another cryostat. We did not try that. But down to 80 Kelvin, we could stabilize only at the 3R phase.
Just two quick questions. Very nice talk. So could you verify the structural transition with some other experimental probe, like diffraction or something? Or is it just
So yeah, as I was sort of responding to Vaiti's question, we actually tried to do X-ray diffraction. The point was our flakes were so small, the routine outer X30 will not be good way to do. So we'll have to figure out a better way.
I see. The next was that you saw some wrinkling. Do you see any signature of flexoelectricity, like coupling to the strain gradient?
One has to measure it. I believe there should be.
Just so speak.
Yeah, yeah.
Comment about the structural determination and difficulty. I wonder if Cryo electron microscopes can be used, because they are evolutionary new developments where you can use electron waves and get local stability. For example, a protein, then you don't need to crystallize a protein, you can take a single protein and get the crystal structure. And even get the position of water molecules. So we have one in IIT Madras, Cryo. So I have been encouraging.
If it can be, yeah, okay, yeah.
Organic materials.
Right.
You can try in our electron.
In fact, there are a couple of TEM studies on this particular material. Yeah, I understood.
Even more sophisticated.
Yeah.
Just you can look at a single molecule and you can see.
Sure.
Go to